So in this session of signals and systems, we are going to study the introduction to the design of digital filters. So let us start. Let us first of all revise the filter equation that we had studied in our last session. And this is the equation between output and input for a non-recursive digital filter. Non-recursive means there is no feedback. So the output at any given point depends on the current value of the input and many of the past values. So how many past values? That will decide the order of the filter. Larger the number of coefficients you use or larger the number of past values you use, in general, your filter will give you better performance. Alright. So for this non-recursive digital filter, you can consider that it is designed if all these coefficients are known, if B0, B1, B2, etc. If all these coefficients are known, then you have essentially designed the filter. The question is, how do we obtain these coefficients? And in our last session, we had said that these coefficients, the sequence of these coefficients also happens to be the impulse response of the non-recursive digital filter. So if you can find the impulse response, you can find these coefficients. Now, how to find the impulse response? From the transfer function that is given to you for a particular filter, you take the inverse Fourier transform of that transfer function and you will get impulse response, and therefore you will get the coefficients. That is what we are going to do. So in this particular session, we are going to demonstrate the design of a low pass non-recursive digital filter. So we will start with the ideal response for a low pass filter. Alright. So consider the transfer function of an ideal low pass filter. So its gain is equal to 1 for frequencies lying between minus omega c to plus omega c, where omega c is the cutoff frequency for the filter. And outside this interval from frequency minus omega c to plus omega c, it is equal to 0. So if you plot it, it will look something like this. So we plot omega on the x-axis, magnitude of the transfer function on the y-axis, and you can see this is an ideal low pass filter, in the sense that if you look at the pass band, which is from minus omega c to plus omega c, the gain remains absolutely constant at 1. And also this is a brick wall kind of response. That means as soon as omega crosses omega c, the gain becomes 0, and if it is less than minus omega c, again the gain is 0. Note that we get negative frequency only because we are looking at the double-sided spectrum. The physical frequencies will of course be from 0 to omega c. Now we have said that we are plotting omega on the x-axis. So what is this omega? This is a digital angular frequency, and we have already studied that it is given by 2 pi f divided by fs or 2 pi k divided by n. You will recall that is what we had studied. Now for any filter, for any signal, the sampling frequency must be greater than 2 times fs, 2 times f. That means f must be less than fs by 2. So if f is less than fs by 2, this fs will cancel, 2 will cancel, and it will tell you that omega is less than pi. So as far as we are concerned, the important range for the frequencies is from 0 to pi. And actually, since beyond omega c this is 0 and less than omega c it is again 0, essentially when we calculate the inverse Fourier transform, we will use the limits minus omega c to plus omega c. But in general, the limit which is significant for the this transfer function will be omega less than pi. Okay, now what is the equation for the inverse Fourier transform? Recall that it is 1 by 2 pi minus pi to plus pi h naught omega e raised to j omega n t omega. That is the equation. Now the range of minus pi to plus pi can be split into 3 parts: minus pi to minus omega c, then minus omega c to plus omega c, and from omega c to pi. Now from minus pi to minus omega c, this is 0. So the lower limit can be simply changed to minus omega c, and beyond omega c this is 0, so the upper limit also can be changed to plus omega c. And between minus omega c and plus omega c, the magnitude of the transfer function is 1, so this part will be equal to 1. So h naught n then reduces to this equation 1 by 2 pi minus omega c to plus omega c. H naught omega is 1 during this frequency range, so e raised to j omega n d omega. And if you evaluate this, you will get h naught n as sine of omega c n divided by pi n. So if the cutoff frequency is specified, you can calculate the impulse response for various values of n, and it will also equal the coefficients for these values of n. Alright, so let us take a specific example by specifying the cutoff frequency. So this is our general equation. Now let us say that omega c is equal to pi by 2. Okay, remember it has to be less than pi. In this case, we are saying that cutoff frequency is pi by 2. So if it is pi by 2, you substitute here, then the equation that you get is sine of pi by 2. For omega c, we have substituted into n and divided by pi n. So what you can now do is calculate the impulse response for various values of n. Now notice that this calculation can be done for infinite values of n, right from minus infinity to plus infinity. It is only when n approaches infinity that h naught n approaches 0. So for an ideal filter, the number of impulse response values will be infinite, which means the coefficients will be infinite. That is for an ideal filter. For a practical filter, obviously you cannot have infinite number of coefficients, so you will have finite. How many you use depends on how good a filter you want. In general, larger the number of coefficients you use, better will be the response. So here, using this equation, we have shown the values for various values of n. So minus 3, minus 2. So if you substitute n into this equation, minus 3, you will get this. Minus 2, it is 0. Note that this is 2. Then sine of pi is going to be 0. Minus 1 is again 0.318. You can do the calculation. Now, when n is equal to 0, you have to solve the limit, which you can easily solve by noting that sine theta approaches theta as theta approaches 0. In that case, as n approaches 0, the numerator approaches pi by 2 n. So pi will cancel, n will cancel, and you are left with 1 by 2. So that will be equal to 0.5. And then for 1, you will get the same value as minus 1, because remember, if n is negative, sine of minus theta is minus sine theta, and n is negative, so the two negatives will cancel. And if n is positive, anyway this is going to be positive. So you will get the same value for 1 as you got for minus 1, and same value for 2 as you got for minus 2, and so on. Okay. So if you plot this, it will look something like this. H naught n, at n equal to 0, you get 0.5. Then h equal to n equal to 1, you get 0.318, and so on. This is how it will look like. And theoretically, this can extend to infinity. Of course, these coefficients will go on reducing as you increase n in both directions. But theoretically, you will require infinite coefficients. So theoretically, n extends from minus infinity to plus infinity. In a practical realization, h naught has to be truncated. That means you can use only finite number of values. Also, another important thing you should note is that impulse response is non-causal. Why? See, what is an impulse? Impulse has a value only at n equal to 0. It has a unit value. Outside this, it has no value at all. So if you look at the negative values of n, the input has no values at all for negative values. So how can you get any output? So therefore, this particular impulse response that you find is non-causal. It cannot be realized by a practical filter. So then what do you do? So as we shall see, what we are going to do is to delay this. See, one simple thing you can think of is simply ignore this. Suppose you ignore this and take only 0 and positive values, then the problem is that effect of large number of coefficients you are neglecting. So you will not get a good frequency response. So if you want a good frequency response, what you can do is, and at the same time keep it realizable, you can actually delay this. So if you delay this, then the values which are lying for negative values will go on decreasing. Suppose this comes here, this will come here, so this is already small. If I delay it further, the values which are lying for n negative, you will find they will have small values. So even if I neglect them, the effect on the filter response is not going to be much. So understand that the theoretical response that you get, there are two problems. One is practically you require infinite number of theoretically you require infinite number of coefficients, and also the impulse response is non-causal, and both these we have to take care. We will again say this. So first of all you have to do is to truncate. So for example, H0n actually can extend from infinity to plus infinity. For obvious reasons, I have plotted for a finite number of n. So minus 3 to plus 3, I have shown this table. Now out of this also, suppose I don't want to use so many values. I want to use only from minus 1, 0 and 1. Then what I do is keep all these 0, which is equivalent to multiplying this by another function which we call as window function, whose value is 0 for all values of n except the ones in which we are interested. And during this time, the window function is constant. This is 1, so 1 into this will be same, 1 into this will be same, 1 into this will be same. So the rectangular window function itself is constant. If you plot this, it will be 0 until it reaches this at minus 1, jump to 1, remain 1, again 1. So if you join all these points, it will look like a rectangular window. Okay, so that's how you do truncation. So let us revise these practical considerations. Ideal filters are not realizable for two reasons. One is infinite coefficients are required, which is not possible. And second is, for the ideal filter, impulse response is non-causal. It cannot be realized at all. So what then is the solution? A practical filter with close approximation is possible by using large number of coefficients. Some applications use something like 100 or 101 coefficients, and providing appropriate delay so that the filter is realizable. Obviously, more the number of coefficients you use, more is going to be the delay. So larger delay, if you can tolerate that, then you can get a good filter response. Okay. So let us look at what this means practically. So again, we are showing the example for cutoff frequency equal to pi by 2. So these are the equations which we have already studied, and these are the values for H0n. Since this cannot be realized in practice, what you do, you shift the whole thing by, say in this case, 3 units. So what is at minus 3, same value you get n equal to 0. So at n equal to minus 3, this is minus 0.106, etc. So here same value is obtained at n equal to 0, because this is going to be a causal filter. So everything shifts to the right. Okay. So all these values are basically copied, but for later values of n. How many later? Depends on how many coefficients you are using. That much delay you have to provide. Okay. So for a practical filter, H omega is, understand that H naught omega, when we plotted it, we assumed that phase angle was 0 for all frequencies, which is never possible in a practical filter. So there will always be some delay. So your actual equation is like this, but we are right now interested in the values, and they are shown. So this table of values essentially is implementing this particular equation. All right. Now that we know what are the coefficients, and we now know how to obtain the so if these coefficients are used, and if you find the Fourier transform, you will get the filter. You will get the transfer function of the filter. Okay, and then you can compare it with the ideal response. So that is what we are going to do. So we'll write a program for that. So this is as usual. Then cutoff frequency you would define. This could be something else. Of course, it will always have to be less than pi. In this case, we have said pi by 2, could be pi by 3, pi by 4, and so on. Then n1 is equal to 3. So we are going to use 7 number of coefficients, which means because it goes from minus 3 to plus 3, remember? So minus 3, minus 2, minus 1, etc. So it will be 2 into n1 plus 1. That will be the number of coefficients. So n is 2 into n1 plus 1. Now initially x holds a null. What we are going to do is to go on calculating and putting the values for the coefficients in this array. So initially we start with the null. Then we set up our for loop, which is from minus n1 to plus n1. So it starts from minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. For that we set up the for loop. Then n equal to 0 condition we check separately, because remember in that equation for the impulse response are therefore coefficients. We had n in the denominator. So unless we check this condition separately, we will get an error saying that denominator is 0. So we calculate the coefficient for n equal to 0 separately. If n is equal to 0, we know that it is omega c divided by pi by applying the limits. We had already seen this. Else x1 is given by this particular equation. Okay. Then you append this x1 to x. So initially you started with null. Now it is appended. This ends. Then you can display x for your convenience. Now you add large number of zeros to this. How many? As many as are required to make the total number of samples for x2 equal to 1024, because that is a good figure for which FFT calculation gives accurate results. But it could be other values also. And these zeros we are going to append to x. That is what we are going to do. So x is equal to x. So this zeros we have appended because we want a good frequency resolution. Because even if the number of coefficients are small, if you add large number of zeros, then you will get a good frequency resolution. So you calculate n1, that is length of x, k equal to 0 to n minus 1, n1 minus 1 as usual. And the angular frequency is 2 pi k by n1, again as usual. Now you calculate the FFT of x, find its absolute value, and you are now ready to plot the magnitude response. So you plot W, YA, line width, etc. So if you plot this for n equal to 7, that is in that program, remember we had said that we are changing from minus 3 to plus 3, but we can change that. So for n equal to 7, you can see you get a response like this. Understand that ideally what we want is a brick wall like this. So obviously in this case, since the number of coefficients are only 7, you don't expect a very good frequency response. Alright, so this is what you get with n equal to 7. Now if you want to improve this, you can increase n. So you have to do a little modification in that value for n there in that program. If you do that and plot the response for n equal to 51, then you'll get something like this. So you can see this is much closer to the brick wall response of an ideal filter. So this is, remember this is pi, this is plotted for omega c equal to pi by 2. So you get almost like a brick, but you got some ringing here. Now this ringing problem can be, this we are getting because essentially we are using a rectangular window. Note that in that program we did not have to specify a rectangular window because all coefficients are multiplied by 1. So multiplying by a window having all values of 1 doesn't change anything. So we did not have to do it. However, if you want to reduce this ringing, then what you have to do is to use some other window function instead of the rectangular function. So as we said, rectangular window function gives ripples in frequency response. So many different window functions have been found by scientists. They are available and they have got, each one has got its pros and cons. I'll just demonstrate one window function which is called as a Hamming window, but you can study the literature and find other windows as well. So in this case, what you are doing is, in that rectangular window, it was suddenly jumping from 0 to 1 and then remained constant at 1. But you get, if you give a more tapered window response, then tapered window rather, then you will find that your ripples are reduced. So this is the definition for the Hamming window. And so what you have to do is to insert the following code after statement number 14. N equal to minus n1 colon n1, then calculate wi, and now multiply x with this wi. Okay, this modification you have to do, and then you will be able to plot the transfer function magnitude response using the window, and you will find that your ripples are much less. Of course, you will have to add code to plot omega versus n, so that will give you window function also. So if you look at this, essentially you are changing the n from minus 25 to plus 25, and you can see this window, if you look at its values as a function of n, they are not constant. Gradually it is increasing, reaches 1, and now if you find the transfer function, you will find that you still get ripple, but this is much reduced compared to the uniform window. Alright, so in this session we have seen how to design a non-recursive digital filter for the low pass function. Similar equations can be obtained for high pass, etc. We'll discuss that in the next session. But what we did was to calculate the coefficients for a given cutoff frequency, and then verifying that when you take the Fourier transform of this, you should get a transfer function which is close to the ideal. And what we have found is that the larger the order of the filter, that is, the larger the number of coefficients you use, better is the filtering action. Also, the ripple in the pass band as well as in the stop band can be reduced by using an appropriate window function. There are many window functions available. We have demonstrated for one window. And that's all in this session.